Okay, so I've been procrastinating making this video because it's quite long, but here are my thoughts on how we can actually create an AGI system which can effectively learn. So I'm just going to talk about three missing parts which I believe current models don't have. And yeah, I'll just explain them further. So number one, we're missing a robust memory system. Okay. Number two, we're missing a predictive loop. And number three, we're missing time scale layers. Okay, so I'm going to explain what each of these are and yeah, how I believe we can put everything together to create a actual AGI system which will learn just like any organism on this planet. So let's talk about this first one first. We need a robust memory system. Let's actually consider what actually makes intelligence first of all. Let's think about this. So what makes intelligence? And there's three key principles that any entity needs to follow in order to become intelligent. So the first idea is the idea that it can perceive its surroundings or its environment. So humans, this is going to be the senses, like you can see, you can hear, you can smell, stuff like that, right? You need to be able to perceive. This is what is going to allow you to get feedback. Secondly, you need to be able to reason. And again, humans can do this. You know, we can see something, we can see two things and reason. Maybe we can see like 1 + 1, we can reason that's 2, okay? And the third thing is you need to be able to evolve. And this is the key thing right now, which LLMs are missing, and in general, agents are missing quite a lot. The ability to evolve just means you can take feedback, you can remember it, and you basically not make like the same mistake twice, if you know. And this is what we are missing. So currently, we can kind of think of LLMs as just a stateless machine, stateless black box, if you will. They basically take in inputs and they give you out more outputs. And LLMs have actually they've been improved. So now, since they're multimodal, they can also just take in different types of inputs. They can give you out outputs. So LLMs can basically perceive, and we can treat LLMs as, I'm going to just call them stateless, let's just call them stateless reasoning models, just so we're clear about what they actually are. Like LLMs themselves are not the AGI, they're just the reasoning models. Think about like your IQ in a way, but they can't evolve and they can't remember stuff that you give them. So that's where we need this memory system. Now, let's just consider OpenClaw for a second, because this is pretty interesting in that it actually shows a first implementation of a memory system using MD files. So when you send something to OpenClaw, let's say you send a message in, it sends it through one of these LLMs, and then it does the task with like whatever tools it has, and then it writes feedback into MD files. And then this repeats either with a heartbeat or your new message, this loop, pretty basic loop, but this is the memory essentially, which allows OpenClaw to feel much more like an actual intelligent entity compared to ChatGPT. The fact it can remember stuff. But using flat markdown files, or in some cases like in RAG style models, when you have a flat vector database and you just take in inputs and you just get the semantic similarity entities in a database, this is not enough. Like MD files, I'm gonna just say RAG, these are not enough. We need a much more robust memory system. So I'm gonna call this a memory management unit. And the idea of this is that, let's just think about it like a black box. We can interface memory and we get out whatever we're looking for, and it abstracts away everything. But within this, you know, we have stuff like timelines, episode or episodic versus knowledge memory, like specific episodes of events compared to the knowledge you gain from that, compared to procedural timelines. This is like short term versus long term. And you could like consider a LLM's context as a short-term memory, but I think it's easier to just think about these as the reasoning models, and we just completely separate the whole memory management systems. And think about it. Memory is essentially the biggest hurdle in order to get an intelligent system, because once we have memory, you can give it some input, pass it through the LLM, it executes with what it just learned, then we can get our feedback, pass it into our memory system. This remembers it better, and then this loop just continues. LLM uses memory it learned in the previous iterations, and it just gets better and better and better. And this is what's allowing it to improve from feedback. Okay, cool. So that's the basic gist for why memory is vital and why we need a much more robust memory management unit. Now, there's a lot of papers coming out right now which are trying out different memory styles, different memory architectures for creating these evolving systems. And so it's a very cutting edge area of research that has a lot of potential. The next thing, let's talk about the predictive loop. Okay, so I've already talked about loops a little bit. OpenClaw again did show us that just a simple loop is enough to create sort of intelligent like behavior. And even in nature, if you think about what a human's doing, you're pretty much always just working on a continuous loop. Like think about like a wild tree loop that just never ends. So the loop that I've come up with is something like this. So you observe or perceive your surroundings or environment, observe, you predict what's going to happen, then you plan what to do, take the action, and then I'm going to come here. Then you observe again, reflect on, compare what you predicted to what you observed again, reflect, and then update memory. Okay, this is the loop I came up with, and then the idea is you just run this over forever, basically. And this is what's going to allow the AGI system to just continuously learn from surroundings. Now, you might be wondering why we're in a predictive loop. Well, this is a pretty interesting fact from even human psychology, the fact that we don't really react. We don't react to our surroundings. We actually predict what's going to happen and then act based off that. And then if our prediction was wrong, this is where the second stage of observing and reflecting comes in. We update our internal beliefs. And another interesting thing is that since we predict, we have two ways of making this prediction come true. So either we can take action to make prediction true, or we can just update our beliefs, or in this case memory, to make prediction true. So we have two ways of doing that, and that is all handled within plan and action stage. And yeah, this is the general idea, right? If you think about it hard, this is also how all organisms work. They all work off a predictive loop. And it's one reason why the simple something like this loop, so observe, react, feedback, like this kind of loop, it seems like what you would want, but it's difficult because how do you get this feedback when you've just reacted? Like, where's your loss function? It's kind of like you observe, you react, as in you perform an action, and then it's kind of unclear what your feedback is. Like, is that good or bad? Whereas here, when you predict, then you clearly predict what you're expecting, and then you observe. You can clearly get a loss function from that. Even if it's not like an obvious mathematical loss function, you can generally just use a reasoning model or something to reflect and get a score of how accurate a prediction was. And the idea, the free energy principle, is that we are trying to minimize predictive error. So we basically want to be able to predict the future as well as we can. It's not just that, of course, because you also have other motivations. For example, what I was thinking is we also want to maximize the reward of an action. For example, let's say you observe your current state. You've just got a message from your boss saying, can you complete task X? Then you predict you can either complete task X and get rewarded, or you can just do nothing and you get fired. If you do nothing and then observe you get fired, well, technically you did minimize prediction error, but that's not the outcome you want, is it? Because you probably want to, like, it depends on what you want, but most likely you want to create some value, and so you would do task X. And so clearly we're not just minimizing predictive error, we're also trying to maximize reward. And another thing we should do is we're trying to maximize information gain. Okay, so this is allowing us to optimize for learning as well. So for example, one thing we could do is, let's say we know how to, so we observe, please do task X, and we've done it in the past, so we already have that task in our memory system. Well, then what we could do is we could just predict that we can just do the task the same way we've always known. Then we'll plan action, we'll get our reward as we want, and we'll also have minimized predictive loss. But there might be a much better way of doing it, which you predicted here. Like, there might be a way to do it 5 times faster. And obviously that has a higher, that has a lower, like, expected reward, because the probability of you actually managing to do it that way is lower. But you also manage, if you do it wrong, you'll learn. And so you'll get a lot of information gain in a reflect stage, and that will help you improve your memory and help you evolve much better. So that's just another metric that is useful to maximize. And there's definitely many more different metrics. I mean, this is basically the entirety of any model, is which functions do you maximize. And so these are basic ones, but definitely this can be expanded in the future. But yeah, this is the basic idea, okay, of the predictive loop. And now let's move on to my final idea, which is the timescale layers. Okay, so how do we motivate this? Okay, and what do I mean by a layer? Well, one layer is one loop. So if you think about how a coding agent works, this can be thought of as a single loop, right? User gives, well, it's always the same loop. I'm just going to bring this loop from above. So this is the loop we're always working with. Observe, predict, plan, action, observe again, reflect, and update memory. This is essentially the loop that we are always working with, and then we just go around again. But this raises a problem. How often do you trigger this loop? Okay, so does it just run indefinitely, as in we trigger it once and it just runs indefinitely? There's no heartbeat system or anything, it's just running constantly like a wild tree loop. Okay, that will work, but the problem is we would end up having stuff like this. Let's say we are told, this is a bad example, like it's hard to illustrate, but let's just say we're doing, we say, write word 1, write word 2, and then, like, I don't know, start a company. I'm just giving examples of tasks we might be given. Okay, so clearly these first two are just super simple tasks. They take less than a second, whereas this final task is much bigger. It's going to take a week or something. And the problem is, if we do everything in a single layer, like we only have one loop, then all of these tasks have the same hierarchy. And essentially, we're treating all tasks slash predictions as if they run on the same timescale. Which isn't really true, right? Like, one prediction might be, I can start this company, get rich, but that's on a timescale of a few months at least. Whereas another prediction might be, I write this essay and I get it marked, or yeah, I answer this math question and get it right. That's on a timescale of much lower, right? A few minutes. And so we need to kind of separate out these different timescales. And this is another thing which I haven't really seen any kind of agent implement right now, but it's actually well known in scientific literature. I don't remember. If you want to search it up, it's something like the Fusey cascade model. And I have done some research on this, but I won't get into that today. I'll get into that in a future video. But the idea is we need to kind of separate out these loops. We need to have multiple layers of each loop which handle beliefs and predictions slash tasks at different timescales. And even in humans, you can kind of see this in the human memory system. If you think about the brain, the higher levels actually handle more higher, like longer running tasks, like your core beliefs, stuff like that. Whereas as you go deeper and lower down, the parts of the brain handle much more operational daily tasks. And even down to the level of like an individual neuron, these run on a timescale of milliseconds. And so even the brain works in a similar hierarchical way. So it's pretty vital that we create a bunch of layers. And what I would propose is that we have a bunch of layers which each have their own loops. So layer 3, let's just say we have layer 2, right? And so we start with the observe current state, whatever, and we get to the predict. Oh, hang on, why did I even do that? Yeah, so we predict, and the idea is we predict what's going to happen next, but then we just delegate down to layer 1, and then we just let layer 1 run until it's complete, and then we observe the output. So layer 1 essentially handles the plan plus action stage, and we've added some new beliefs into via layer 2 as a higher guidance. And we delegate down to layer 1, and then we just observe again what layer 1 did, reflect, and update memory. This is the idea. So it's a recursive system, and then I'll just replace layer 2 with layer n, and replace layer 1 with layer n minus 1. The idea is we can just keep on adding layers on top of each other to keep on increasing this timescale which this agent can run at. And if we think about coding agents right now, they can almost be thought of as a 2-layer system, where layer 1 is just the LLM reasoner, and then the LLM reasoner has its internal architecture, obviously, which is its own kind of loop. Words come in, produces an output, just call it that, and then they just get fed back in. Same kind of thing. And then layer 2, this will observe, user message. They don't really run off prediction, but it's a similar kind of thing. They I'll just say plan. Well, that's bad actually. Yeah, I'll just say predict, and then we'll say delegate down to the layer 1, which is the LLM, to actually get the tasks done. Then they complete the action via tools, and then they observe, what was changed in the code, what needs to be done, reflect, and then, the update memory stage in this case is kind of just updating the context of what's going on. In Claude Plan mode, they actually kind of increase this to the more full layer where they update context via MD files, storing the MD files, stuff like that. Plan mode is almost a complete layer. And then OpenClaw can even be thought of as a layer on top of these coding agents. So let me just write coding agents. And then we can just have OpenClaw, which is like a layer on top of this. And then OpenClaw is also triggered autonomously by the heartbeat system, but you know how that's all fine. But yeah, this is the idea. And so my idea is that we generalize this layer system, then we can add many more. I've done some research and I believe the ideal number of layers is somewhere around 3 or 4. But obviously this will have to be tested out in actual development and testing. But yeah, this was my overall thoughts on how we can create this AGI system. And then I have a few more thoughts which I want to get into later, because this whole layer system is pretty similar to how OS is actually scheduled processes on a task. And combine that with the fact that memory is pretty similar to how OS is actually handle memory with the different tiers, cache, RAM, secondary storage. I think creating an AGI is very similar to actually creating a operating system, and there's a lot of analogies between the two. So creating them would be very there's a lot to learn there too. But I'll make a few more videos on this. This whole mental model of how an AGI is created is also interesting to understand how human intelligence really works at a fundamental level. And I want to make some videos covering that too. I mean, let me just explain one thought I had earlier here. So IQ can actually be thought of as the black box reasoning models, like IQ as in what people generally measure their intelligence on. I actually think IQ is much more similar to what a stateless reasoning model is. Like IQ generally tests your reasoning abilities, but that does not fully determine someone's intelligence, because memory is almost just as important as someone's IQ score. Like the ability to structure information in your brain well. If you can do that, you don't need a truly good reasoning system. If you have incredibly structured memory, if you have a really clear mental model of how everything works, then that's like a whole nother missing part, which I don't think intelligence tests. Well, they probably test it a little bit, but yeah, that's like an interesting thing. And it's also why you might observe people with not that high IQ are able to do some pretty interesting and really smart stuff, and people with really high IQ sometimes don't seem to be doing too much, don't seem to be, grasping things as well. That's like a missing piece, I think. But yeah, these are just my current thoughts. Going to be making a few more videos coming out soon. Thanks for watching, and I'll see you guys in a future video. Bye.